Welcome to the chapter 2 of Algorithms Crash Course. In the last chapter, we learned how to evaluate and compare efficiency of algorithms and how to represent that evaluation of efficiency using something called the big O notation. In this chapter, we will learn binary search algorithm using Python. Now, searching and sorting are the two greatest obsessions of computer scientists. Google, the biggest tech giant of our age, was able to beat its competitors in the 90s because it has the most efficient sorting algorithm that arranges or sorts millions of web pages so that you get what you are searching for on the first page of the search results. That is not an easy problem to solve. Same goes for the algorithms of Amazon, Netflix, and all of them owe their success to sorting algorithms. We won't learn sorting algorithms today. Today we will learn searching algorithms, which is what you do once you have a sorted list. So before we get into algorithms, we need some background in data structures. The most common and simplest data structure that you will be working with is an array. You can create an array in Python by simply writing the name of the array. I will name my array x and equals to sign, and within square brackets you can write a list of values separated by commas. So an array is just a series of items or a list of items. You can store multiple values in one variable, and you can access the individual elements of an array in Python like this. You can write x, and within square brackets you can write the index number of the element you want to access. So if you write x0, you get the first element of the array, and if you write x and within square brackets you write 1, you get the second element of the array, and so on. A useful hack to know in Python is that to access the last element of the array, you can write x, and in brackets the index number you can specify it as -1, and to access this second last element of the array you can write -2, and so on. In Python you can also slice an array. For example, I can create another array y which is equal to x to colon. I will use the colon operator 4. So the value of y is 78 and 79. It is a sub array of x. So that's how you can slice an array. But I actually lied to you. This is not an array, it's a list. So what's the difference between an array and a list? Well, Python doesn't allow us to use pure arrays like other programming languages. Instead, it provides us with a special data structure called a list. A list is basically an array with superpowers. And arrays have fixed size. Lists don't have fixed size. You can keep adding elements in a list. It is easier to access and modify elements of a list than arrays. The fundamental difference between an array and a list is that an array can only have elements or items of the same data type. So you can have only integers or only string variables. But in a list, you can have, for example, a string variable, an integer, a decimal number, and a boolean value all in the same list. So you can have elements or items of different data types in the same list. But let's pretend for the sake of this tutorial that this is an array. So we have an array with 5 items in it. Let's say I told you to write a program that lets the user input a number. Suppose the user inputs 78, and then the program searches that number in the array and returns the position of that number or the element in the array. How would you write that program? The obvious algorithm that comes to mind is that the algorithm could go through the entire array one by one and check if each element matches the user input. Let's write a function for that. I will name this function simple search. Add 2 parameters to this function. The first parameter will be our array, and the second parameter will be the user input or the number that we have to search through the array. And then I will use a for loop to go through the entire array for I in range of length of our array. Now what is range and len here? Let me explain. Len is a Python function which returns the length of an array. For example, if I write len x, then we get the length of the array, which is 5 because the array has 5 elements. And range is a Python function which turns a number into a list with the length of that number, starting with 0 as the first element. If I write list, then you can see we get a list with 5 elements starting with 0 and 1, 2, 3 and 4. Within the for statement, we will write some if statements. The for loop goes through the entire array and searches if any element matches the user input, and it returns the index number or position of that element if that element is found. Now let's test the function that we have created on our array x, which we had defined earlier. If I write simple search, and in the parentheses we keep x, which is our array, and let's say we want to find the position of the number 89, then I will write x, 89, and our function returns 3. Similarly, if you want to search the position of 67, then we can write simple search x, 67, and it returns the index number of that element correctly. Now, can you tell me what is the efficiency of this algorithm in big O notation? I will give you a hint. Simple search is also called linear search. Its time complexity is O(n). But why? Recall that time complexity is simply the number of steps an algorithm requires. 5 elements. Since we have 5 elements in our array, in our list, the best case scenario is that our algorithm can find what we are looking for in just one step. If you are lucky and what you're searching for is the first, but the worst case scenario is that the algorithm will take 5 steps or n steps if the array has n elements. Always remember that big O notation always expresses the worst case scenario of an algorithm. So linear search or simple search is not a very efficient algorithm. It may work fine for small arrays and lists, but if you have data structures, or if you have arrays that have millions of elements, it's a very inefficient algorithm. So we need a faster searching algorithm. Luckily, we have a fast searching algorithm and it's called binary search. But there is one condition for using it. The items in the array need to be sorted. Sorting algorithms will be covered in the next chapter. If you haven't noticed, the arrays that we have been using in this tutorial are already sorted on purpose so that it will be easier for us to apply the binary search algorithm. Before we implement binary search algorithm in Python, let me explain to you how binary search actually works. Here's an example. I will think of a random number between 1 and 20. How many attempts would it take you to read my mind? Worst case scenario, it will take you 20 attempts, and best case scenario, it will take you 1 attempt. That's because you are using a simple search algorithm. You go through every number from 1 to 20. Whether randomly or serially, it doesn't matter, but you have to go through every number from 1 to 20 to check if it's the number that I have in mind. But if in addition to telling you that you have guessed the wrong number, I also tell you whether your guess is too high or too low, things get easy. Your first guess should be 10. If I say too high, you only have to guess between 1 and 10. And then you should guess 5. And then if I say too low, you will only have to guess between 5 and 10, and so on. It's probably going to take you 5 attempts in a worst case scenario. This is how binary search works. It keeps splitting the array into halves until it finds the searched item. Let's look at the implementation of binary search algorithm in Python and try to understand how it works. Let's create a function. I will name it binary search. And our function has two parameters, the array and the item that we are searching in the array. Then we define a variable low and set its value to 0, which is the index number of the first element in any array. And then we define another variable high and set its value to the length of the array minus 1. This is the index number of the last item of any array. Initially, we have our lower limit as the first element in the array and our higher limit as the last element in the array. We will be using a while loop. So while low is less than or equal to high, the while loop will run until it returns the index of the item that is being searched. Within the while loop, we define a new variable mid, which is the midpoint between the high and the low. I will use the integer function, and within the integer function I will write low plus high and divide it by 2. Suppose we get 2.5 as the midpoint between our lower limit and higher limit. 2.5 cannot be the index number of any element of an array, right? So we have to transform it into an integer. And if you use the int function, then you will get a whole number instead of a decimal number. Once we have the mid variable, then we will get another variable, guess. And guess will be the element of the array with index number mid. So once we make a guess, then all you have to do is check if the guess is too high or too low. How are we going to do that? We will use if statements, of course. If guess has a value of item, if our guess is correct, then we will return the index number of the item that is found. But if our guess is greater than the number that the user has searched for, then we will reduce the higher limit. We will make it mid plus 1. And if our guess is smaller than the number that the user has searched for, then we will reduce our lower limit. And low will be mid plus 1. Outside our while function, at the end of our function binary search, I will write return none. If we are not able to find what the user is looking for, we will have to return none. Right? Now let's test our binary search function on our array that we have been using. I will use the binary search function, and in the parameters I will write first the array that we are searching for, and suppose we are looking for 86. What is the position of 86 in this array? Then we can see that it returns the right number. The binary search algorithm has a time complexity of O log n, which is very fast when compared to the algorithmic efficiency of simple search, which is OM, if you recall the last chapter. But it only works if the data contained in the array or any data structure is sorted. Otherwise, we will have to go with the slower simple search algorithm. In the next chapter, we will learn two important algorithmic paradigms: divide and conquer and recursions, which will prepare us for learning sorting algorithms. See you in the next video.